Thanks so much, Don. We're going to turn it over to Richard now to begin today's first presentation. Richard, over to you.
All right, good morning. My name is Richard Perez, and I'm going to talk about very high penetration of photovoltaics on our energy resource grid. What I'm presenting today is a product of international research. Many people in the US contributed, and in Italy contributed to what I'm going to present today. The question that's preoccupying some of you is, do we want to see this much solar in rural New York? And we're going to actually quantify and put that this much in perspective. But before doing that, let's contextualize the discussion. So we have a problem. It's been eclipsed a little bit by the corona problem, but the corona will go away. But this bigger global warming problem will persist and grow in the future. The good thing about this problem is that almost 90% is traceable to energy consumption, one form or the other. So if we resolve the energy question, we will likely resolve the problem as well. So it's good to take a look at the way we use, how much energy we use. So the world consumption of energy on the planet in all the forms, electricity, transportation, buildings, industry, is about 19 terawatt year per year. A terawatt year is a big quantity of energy. It's trillions of kilowatt hours, a unit you may be used to. And how do we meet that demand today? We have big coal reserves. We have uranium to fuel the nuclear power plants. We have petroleum, and we have natural gas. So putting them together, we have many years ahead of us, but they are finite and they will go away someday. So that's a problem in itself. Then we have renewable resources that could do the job. This is the wind potential every year, so it's pretty big. It could actually meet the demand of the planet several times over. You may have heard of wave energy. So it sounds powerful and big, but if you add it up on the planet, it's not very big. It's a byproduct of wind, so it's a small resource. We have something called ocean thermal energy conversion, exploiting the difference in temperature from the top and the bottom of the ocean. That's not very big. We have biomass, so you've heard of corn ethanol and crops for energy. This is very disappointing because even if we converted all the crops to fuel for energy, they would not be enough on the planet to power the earth. We have hydropower, and hydro is limited by the number of rivers we have to exploit, so it's not a giant quantity. We have geothermal that can only work with current technology only in a few places on the planet, so it's not large. And there is also tidal power. Works in New York City. There is a small power plant there, a couple places in the world, but it's a very, very small, limited quantity. And then we have the solar resource, and that's every year. So when you compare them all, it doesn't even compare. One is orders of magnitude bigger than the other ones. So for me, it's not a basket, it's not a mix of energy where you put a little bit in each to solve your future problems. Solar is it. It's much, much, much bigger than everything else combined. So we have a big solution between solar and maybe wind. And the instrument to transform that solution to help us exploit the energy is photovoltaics. And the good thing with photovoltaics is that it's becoming the cheapest way to make electricity today, by far. So this is the cost of a PV module since I started working many, many years ago. And it's not going back up, it's going down. Today, it's about 50 times cheaper than when I started working. And my friends in the PV industry tell me that 2-3 years from now, it's going to be 100 times cheaper. It's going to be very, very cheap, very low cost to make electricity. So we have a big solution. We have a low cost solution. but it's not growing as fast and as smartly as it could. And there are two main reasons for that. One is that the resource is intermittent. It's driven by the weather, by the seasons. So it's not something that you can turn on and off all the time. And the other one is regulations that are ill adapted to take advantage of that intermittent resource. And those two things kind of feed on each other to deliver something that doesn't quite work today. So let's look at intermittency. So this is the production of a solar power plant on a partly cloudy day from morning to evening. So as you can see, it goes up and down when the clouds go in front of the sun and back up. But this is what we need on the power grid. This is the demand of, that could be Buffalo, New York on that same day. So it doesn't quite fit. And as a result of that intermittency, solar is stuck into some marginal position when it could have a grid dominant position if we transform it. And currently that marginal position, with the solar industry growing and the grid operators having to manage that intermittency, it generates tensions between the utility and the solar industry. And that tension manifests itself in several places, like a moratorium on net metering and that kind of thing. So, and this is the intraday problem, the biggest problem by far. And you may have heard of that famous duck curve in California, where you put more and more PV on the grid and you create huge ramps that have to be managed. But this is the small part of the problem. The bigger part of the problem is multi-day intermittency. So this is the solar supply somewhere in the Northeast US. So you have good days and bad days, cloudy days with no supply, good days with plenty of supply. And what we need is something that's available 24/7, 365 days a year. So if we are serious about transforming all our current generating resource into PV and maybe wind, we have to be able to transform solar into a firm, dispatchable, 24/7, 365 available resource. So how do you do that? The way to do it, the way that works, and everybody is focusing on that today, is energy storage, batteries and other forms of storage. And physically, it works perfectly well. When you have excess, you put it in storage, and when you don't have enough, you take it back from storage. There is only one problem with that, is that whereas intermittent PV is very, very cheap, it's below grid parity, it's the cheapest way to make electricity today. Transforming it with storage only to become firm, dispatchable 24/7 is hugely expensive. It's unrealistically expensive. And here I'm using the least cost projections of battery costs for 20 years in the future. Even then, by taking the most optimistic projections, it's not going to work unless we think of something that's a little bit counterintuitive. We overbuild the solar and wind resource and we curtail them. By curtailing, I mean purposefully, by design, we throw away some of the outputs when we have excess. And when we do that, here on the x-axis, that's the proportion I'm going to curtail from that resource. Something really interesting happens. So the red line, the white line is how much I would pay for my kilowatt hour if it's firm 24/7. The red line is the contribution of the photovoltaics, and the blue line is the contribution of storage. And you see that the red line goes up because I overbuild, so I pay a little more for PV, but the blue line goes way, way, way down. I can minimize my storage needs by very much, and I reach a point where I can actually consider to do the whole thing with PV at a reasonable cost. And we've been studying that in several high visibility research projects around the world. we have a project in the central US, which is led by Clean Power Research, by my son at Clean Power Research. And here we have a solution at the horizon of 2040 with 55% PV, 40% wind, and 5% natural gas to do everything at a production cost of less than 5 cents per kilowatt hour. So that's less than what they are paying today to generate electricity from conventional resources without even counting any environmental benefit. We've studied a couple of Caribbean and Indian Ocean Iceland grids with 100% PV solutions, and then we can come down to also very low cost for a pure solar solution that would power not only their electricity, but also the transportation sector and their building sectors. And my colleagues in Italy applied that to the entire Italian grid, and they came up with a solution about over 50% PV, 30% wind, 10% hydro. They have a lot of hydro in Italy with the Alps, and 8% natural gas to reach also very, very affordable production costs. So this thing is very solid. There is a lot of research to back it up. The thing that's not in place today is that the solution to get us there cannot be deployed today. It's not monetizable. Nobody will pay any solar producer to curtail their output and overbuild. It's not in the DNA of the system. So we're kind of stuck here where we could go there. And I was at a meeting a few weeks ago, and the title of the panel I was on was "What steps are government taking to allow integration of renewables into the power supply?" And the first thing I said was, what steps should governments be taking? Because they're not taking the right steps yet. Obviously, the solution is less technological than policy and regulation dependent. So the first thing that should be done is to monetize firm kilowatt hour instead of monetizing unconstrained kilowatt hour as we do today. So the monetizing firm kilowatt hour would mean that you would embed the storage and curtailment and possibly geographic dispersion cost into the remuneration of those solar power plants. Firm dispatchable PPAs would do the job well. And we have to move away from the current models that are supporting the industry, which is the unconstrained PPA. So you provide a power purchase agreement for every kilowatt hour that the plant will produce instead of firm. We have value of distributed energy resource in New York, and we have net energy metering for people on their roof. All that is monetizing unconstrained kilowatt hours. So we have to change that paradigm, and the sooner the better. Second thing to recognize is that we need firm power generation, not with respect to any particular customer, but with respect to the grid at large. That means that we have to evolve from a deployment process, which is pretty much customer driven today, to something that is grid operator driven. But that doesn't preclude developer or customer ownership like we have today. There could be a lot of benefits accrued to PV developers and customers who want to deploy PV. Just the decision and management would have to go from customers to grid operator. So that paradigm shift from customer driven to grid operator is something that I experienced myself over the years. I was a huge proponent of customer driven solar. This is the solar house I built in 1995, which had the first interconnected PV system in upstate New York, before even it was legal to do so. The net metering law only appeared in 1997. So, and I was a huge proponent of, I want my own system, I want to do my own energy. And back then solar was small, and marginal solar didn't even occur to me that it was not the way of the future. 3 years ago, we upgraded to a much bigger system because it made economic sense to us. And I even put a battery to supply power during outages. And we have enough electricity that I can power an electric car with it and commute 100% on solar. So effectively, my wife and I are net zero, but the system made it very easy for us to do that. The system is geared for customer deployment. We had net metering, so we have high value for all the solar electricity we produce. We have a big tax credit from the feds, another one from New York. We have a rebate. NYSERDA gave us $1 a watt for our roof system. I have an EV rebate for the electric car. And everything that didn't come from tax credit or rebates, I borrowed from NYSERDA at a very, very low interest rate over 20 years. So basically it was just a good financial deal for us. But the big question is this the best way to big solar? And the answer is clearly no, because all those customers you see downstate or in any major city and many places, they just cannot do that. And if I solve the suburban people who can do it problem, it's a small part of the problem we have to fix. So currently the system is good for solar at the margin for some, but it's not the big solar for all. So how do we transition from marginal solar to a big solar paradigm? So as a customer, I wish I had the choice of opting for a much smaller system, just enough to give me my islanding resiliency. So when I lose the power grid, I can still operate in my home. But I would have been glad to own or lease the rest somewhere where it makes more sense in a larger power plant. That thing is connected to the grid and give the control where to deploy and how to manage to the grid operator. So they have a much better sense of how to deploy the storage and curtailment resources over time. I'm still connected to that grid, so I'm still can claim my 100% net zero part. However, the system is now designed to feed all the power needed wherever it is needed, including to the big cities of the state. So for that, we have to adapt the monetization regulations. Otherwise, currently, it will not happen. And the big thing is to monetize firm power generation instead of monetizing unconstrained generation as we have today. That means enabling oversizing and curtailment of the systems. And the other thing is move away from the behind the meter economics, either through net energy metering or community choice aggregation that we have today, where it's driven by all behind the meter numbers and unconstrained production. So since we are talking about oversizing, here I'm talking building more PV than we need by close to 50%. Then comes the issue that is a concern for some of the audience today. Where do we put the stuff? How much space would we need to do 100% PV? So for the US, if you add it all up and you use the best technology that we're going to have available to us in the next 10, 15 years, it's going to take a big area, 8,500 square miles of PV for the US. And here I assume powering all the electricity and oversizing by a factor of 2. But if you put it in perspective, that 8,500 square miles is not much compared to everything else we use the ground for in the US. It's about between 1 and 2% of cultivated crops. It's about the size of high density urban development. So putting in perspective, we're not talking about paving the entire country by far. And also, we don't realize that we are already using much, much more space than that for energy today. Just taking an example of hydropower, We have covered 15,000 square miles of artificial lakes, of reservoirs in the US, killing ecosystems to produce just 5% of the US electricity. So we have a technology that we think is clean and all that, that uses twice the amount that PV would need to produce only 5% of our needs, whereas PV would use half the space to produce 100%. So just put that in perspective. Let's get closer to New York. So that's the land distribution in New York. And if I look at a scenario comparable to the one that emerged from our MISO Minnesota study, where we would have 55% PV, 40% wind, mostly offshore, 5% natural gas, and a very low price of generating electricity for New Yorkers. That's how much PV I would need in the state to do the job, to transform all the electricity sector into PV, 460 square kilometers. So that's a small fraction of the urbanized space in the state, if you put it in perspective. This is the number if I were not only doing the electricity, but also doing the transportation sector, converting all the cars and trucks to electric and supplying them with electricity from photovoltaics, and also converting half of the heating HVAC to heat pump based system that would be powered through photovoltaics electricity. So that's not a big number, 900 square kilometers, compared, for instance, to cultivated crops, hay and pastures. Also, let's keep in mind that in New York and many other states in the eastern US, what we call forest today, and if we look 100 years back, it was not forest, it was something else. That new forest grew by leaps and bounds in the last 100 years. So taking a small fraction of that may not be an unthinkable thing to do. Let's get closer to Niagara County. We were supposed to be presenting right into the middle of the county, so that webinar was centered on the issues of Niagara County. So let's look at the same scenario. So the land cover is a little bit different in Niagara County, many more acres of hay and cultivated crops and less forest, and quite a bit of urban development as well. And I'm going to assume that the New York requirements for energy are prorated not by population, but are prorated by surface area. So each county would provide their share for New York based on their surface area. So that's the bottom line for Niagara County, 5 square kilometers worth of PV electricity only 10 square kilometers if we do everything with the PV, wind, and just a little bit of natural gas for flexibility. So if I look at the extent of that surface, it's about the size, this is 8 square kilometers. That's the Robert Moses reservoir that was artificial reservoir built, I think in 1960 to regulate the Niagara power plant. So that's just covering that could solve 80% of the issue, just that, to put it in perspective. It's also about a little over 1% of the pastures and cultivated crops in the county. So it's no big deal. And it's a small fraction of the urbanized space. So between everything, there is ample space to deploy the resource. Even if we went to a solution which is 100% PV, scrapping natural gas and wind, there would still be tons and tons of space. So the next thing that government should do, in addition to try to think how to monetize firm power and switch from a customer to a grid operator, is to ask where can we deploy intelligently the resource, work with a grid operator and find out where the space is to deploy that the most intelligently. And one thing which is interesting to note, if we move to a very high, ultra high penetration wind and solar for the state, and delivering firm power generation, dispatchable power generation, there is no need to re-engineer the power grid fundamentally as is being proposed. We don't need a super smart new grid with people selling, prosumers selling to consumers and all that. If you make the PV and wind resource dispatchable, they become functionally equivalent to conventional power plants. So they can just be connected to that grid and supply power to New York and other states. And then we can really tackle that bigger problem that's will come back maybe in a year and a half on the front lines. So that's a big solution. I hope you can appreciate it. I hope you can help us move away from the current perspective, which is solar is a marginal niche market. So that perspective is not only the perspective of the conventional industries today that belittle solar, but it's also a result of the way we have been trying to deploy solar in this country that keeps it marginal. So on this, I thank you for your attention.